In this video, we are going to study about the determination of velocity of ultrasonic waves in a liquid using acoustical grating. Let us see what is the principle of this. When ultrasonic waves propagate through a liquid, when ultrasonic waves are propagated through a liquid, the rarefactions and compressions produce periodic variations in the density along the propagation path. So, whenever the ultrasonic waves are propagated through a liquid, the compressions and rarefactions which will produce, those are in periodic variation in the density along the propagation of the path. So, the reflected waves and propagated waves forms stationary wave pattern in the liquid, and hence the nodes and antinodes are formed. So whenever it propagates through a liquid, the reflected waves and propagated waves forms a stationary wave pattern. That is, a nodes and antinodes are formed. So this will produce a opaque and transparent regions in the liquid due to the nodes and antinodes. So thus the liquid behaves in the same manner as the ruled optical glass gravity is known as acoustical grating. So whenever the transparent or opaque regions will be formed, thus the liquid behaves in the same manner. That is it forms a grating like a ruled glass gravity, that is known as a acoustical grating. Okay, see how it will be, how the pattern will be. Okay, it shows the diffraction pattern in the field of view. The apparatus consists of a laboratory spectrometer and an ultrasonic liquid cell along with the RF oscillator. The construction will have all this. Now the ultrasonic cell consists of a regular double-walled glass tank that is filled with the liquid and the piezoelectric crystal which produces the ultrasonic cell waves. See, there is a crystal also which placed in a liquid. Okay, so the double-walled glass tank that is used to circulate water at different temperatures, so that the ultrasonic wave velocity in the liquid can be determined at different temperatures. So we are circulating the water at different temperatures so that we can obtain the velocity of ultrasonic waves in that liquid at different temperatures. Okay, let us see how the working will be. When a parallel beam of light is incident normally on the rectangular column of the liquid that is in the ultrasonic cell. So a parallel beam of light is incident on a particular water tank as a glass tank. Meanwhile, the crystal is connected to a RF oscillator that produces the oscillator will produce the ultrasonic waves travel through a liquid and are reflected back and form a stationary wave pattern that has a nodes and antinodes. Then the acoustical grating is formed. So whenever the diffracted light is focused by the telescope, and the diffraction pattern can be viewed, that can be seen by spacing. Now the angular separation theta is measured. So how we will determine the wavelength, determination of wavelength of produced ultrasonic waves. So from that grating, we are observing A plus B sine theta equals to m lambda. That is applicable for acoustical grating also. So here in this case, A plus B equals to lambda by 2, lambda A. So lambda A, that is the wavelength of ultrasonic waves, and lambda, there is a wavelength of light, and m, there is the order of maxima, that is the nodes, and then lambda u equals to 2m lambda by sine theta. Okay, now how the determination of velocity will be means, we know that v equals to n lambda, that's a vu means ultrasonic waves wavelength, lambda u means wavelength of, velocity of ultrasonic waves and wavelength of ultrasonic waves. Now vu equals to n into lambda u will be replaced by that value 2m lambda by sine theta, where n is the frequency of ultrasonic waves. Okay, like this we can determine the velocity and frequency of ultrasonic waves. And next, let us see what is the non-destructive technique. So ultrasonic waves are extensively used for non-destructive testing of a material, that is detecting the defects, flaws which present inside the material without disturbing the structure of the material, that is the material properties. Okay, so this ultrasonic non-destructive testing is used for a material, that to find the flaws, to find the defects in a particular material without disturbing the structure of the material, without disturbing the properties, physical properties of a particular material which we are taking for the test. So there are several methods to test the material. Among them, that is the pulse method most popular. Okay, so there are several methods including this non-destructive technique, but the most popular method used for non-destructive technique is a pulse echo method. There is a pulse echo method, pulse echo system. Okay, let us see what is the pulse echo system and what is the theory behind it and how it will work. If there is an air bubble or a crack inside the specimen to be tested, the ultrasonic waves are reflected back due to the mismatch of acoustical impedance. Okay, so whenever we'll take a specimen. Okay, if there is an air bubble or a crack inside that particular material which we are taking for the test, the ultrasonic waves are reflected back due to the mismatch of acoustical impedance. So that is the recognition of there is a flaw, there is a defect inside a material. Now, how it will work, how it will detect the flaw means a strong pulse of ultrasonics is sent through the specimen to be tested. At that location of flaw, there is a change in acoustical impedance and hence the pulse is partly reflected. So some part of the pulse will be reflected, hence it is a weak echo pulse. So on the incident pulse A, the echo pulse from the flaw B and the pulse reflected by the other end of the specimen C are seen in the screen of a CRO. That is a cathode ray oscilloscope. So we are incidenting a pulse A. If there is a flaw, the reflected beam is B, and by the other end of the specimen C, that is C. So these three can view by the CRO. Okay, and next, if the specimen is free from any flaw, there will be only two pulses. If there is no flaw, there is a and C only. That means incident and reflect, final wave which we are getting the output. The distance from A of echo pulse B that indicates the nature and location of flaw inside the specimen. So if there is a flaw, we will find a B. If there is no flaw, we didn't have B. We have only incident and the output. Okay, see in this diagram there is a specimen. If there is a flaw, some portion of light will be reflected. Okay, we will observe like this, and we are using a transducer. Say in this is a CRO. Okay, this is a frequency generator, this is a transducer, that means transmitting transducer and receiving transducer. Whenever there is a flaw, it will be like this and it will be amplified. Okay, so let us see what are the advantages by using this pulse echo system. Means minute flaws can be detected and location, nature and size of the defect can be accurately determined. Really, it is a good advantage by using this. So even though these good advantages, there is some disadvantage. What are those? No permanent record of flaw can be obtained as it can only be observed on the screen of CRO. So there should be a good mechanical coupling between the piezoelectric crystal and the specimen to be tested. So these two are the disadvantages of pulse echo system. Okay, so let us see what is the to find the distance. If the v is the velocity of ultrasonic waves in a material, then the distance d of the defect from the top surface of the object is given by how? Okay, that means what is the distance between the flaw and incident pulse means d equals to vt by 2. So this is the distance find to be the flaw. Okay.